greater care and detail, because even the question of what is a textbook, what kind of school systems were present, and whether they were only in matas or various versions are very important questions. And to the point about numerals, and since some of you seem to be surprised by the numerals and words, we should remember that the Indian mathematics actually develops a whole system of meaningless words to stand for numerals, which makes it very easily, which made mathematics verbal. And I don't think that's very exotic. I mean, we can see various interesting connections, but it also has great learning significance for learning mathematics. So thank you for raising all these questions. I now invite Professor Verma.
I also have a lot of disclaimers to make, but I should run through them quickly. Basically, the title is a bit misleading, because from the time that I had to submit the abstract to the actual writing of the paper, the whole thing changed, so I seek your indulgence on that. Briefly, to give you an introduction, I taught physics at the University of Delhi for 40 years. And about 15 years ago, I got interested in questions of methods of science and philosophy of science. And that was, therefore, when I came to the workshop seminar last year, I used that as an occasion to work out what was really bothering me then. And that was the charge by people like Russell and Hume about how the method of science could never be considered to be leading to reliable knowledge, because it depended upon the method of induction. And this disturbed me, after having spent a lifetime doing physics, to be told that you've been chasing a chimera. So in the first, I used the opportunity of the last seminar to try and work out this particular demon in my mind. And it turned out that in the course of trying to prepare, I came across an answer that had already been provided by the Buddhists and the Jain philosophers almost 2,000 years ago, which said that the argument which says that theories based on induction cannot lead to reliable result is itself an inductive statement, because it uses the fact that theories based on induction have kept on failing over the last whatever number of years. This does not guarantee that they will keep on failing in the past, or if you argue that they will keep on failing in the past, you are guilty of using the same argument that you are using for proving that such theory. So that was personally very satisfying, and I thank the organizers for at least allowing me to look into this question in greater detail so I could talk to a group of philosophers. So I have another demon which bothers me for this seminar, which I don't have a solution to, but I can just point out what these problems are. You see, the last 6 years I've been working as an advisor to Ambedkar University, and unlike my previous job, this has meant that I'm surrounded by a sea of social scientists, as I think I am today as well. So I always knew that there were problems between the social scientists and the so-called natural scientists, but I didn't realize the extent of the prejudice and the animosity of at least a representative sample of social scientists against the methods and the discipline of science. And this was to be matched by the fact that the people, at least those social scientists who seemed to be inimical to science, displayed an almost innocent ignorance about the developments in science, particularly in physics, over the last 100 years. So that was the origin of the title, 100 Years of Physics. I also chose it because I thought I'd use this in memory of Gabriel Marquez, who died recently, whose most famous book, 100 Years of Solitude, inspired me in many ways. Although I wanted to build a connection between what I'm going to say and what his book was about, but I don't think I'll have time for that. So how do I work out this particular demon. Why? By asking, why is it that social scientists seem to be so inimical to the methods of science when so many of them are ignorant of what science has done in the last 100 years? That is the basic proposition problem that I'm posing before you. Beg your forgiveness for that. However, if you look at the situation in India, and that's what I'm talking about, so this is rooted in the Indian condition. I'm not making a general statement. It is known that almost 65% of students who start class 1 drop out of school by the time they reach class 10. And of the remaining 35%, roughly half go on to do higher secondary physics or chemistry or mathematics, or choose science as a subject, which would suggest that almost all our future social scientists are going to grow up with a knowledge of science which is based on class 9 and class 10 science. So in order to answer my question, I would therefore urge that we look at the structure of the class 9 and class 10 curriculum in Indian schools in science and see if a possible resolution to this problem lies there. I don't think I will go into everything over here, but just briefly tell you that the curriculum document put out by NCERT tells you what is taught in class 9 and 10. It also gives you a description of the philosophy behind, or at least the vision with which these topics are taught. And it makes beautiful reading, although it makes me a little cynical. Being a cynic, I don't know how much of it will actually translates into practice. So it talks about science being a growing body of knowledge, it being not a finished product, that is, pedagogy should be hands-on and inquiry-based. And then there is a statement that there should be a reduction in the content load, and followed by an enigmatic statement that it is better to uncover a little than to cover a lot. So you can make what you will of that statement. Anyhow, we heard yesterday, for example, that surprisingly, it also says, probably because of, on the basis of experience with the authors, that you must acknowledge that the process is more important than the product, something we are hearing for the first time from curricular framers who control Indian education. But I believe that if they had heard the statement made in one of the sessions yesterday, that the process is the product, I'm sure that would also be included in that preface as well. Now, if that said, let us look at what is taught in class 9, because this is crucial to the rest of my argument. What you teach is basically mass, concepts of mass, matter, states of matter, atomic structure, Newton's laws of equation, conservation of momentum, gravitation, work, power and energy, Archimedes' principle, and sound. This is class 9. In class 10, you teach electricity, Ohm's law, magnetism, optics, reflection, refraction, dispersion, and scattering, and that is all. That's the end of, I'm talking only about the physics part of the class 9, class 10 curriculum. Now, the thing to notice is that there is hardly any post-Newtonian development included in this. Not even a mention of Maxwell's equations. In fact, there is nothing included here which was not known more than 100 years ago. So our class 9 and class 10 syllabi, in physics at least, are ignorant, or leave our students ignorant of all what we would call developments of physics in the last 100 years. And I don't know, I haven't carried out this survey, but I wonder if this is true of the other disciplines we teach in class 9 and 10 as well. It'd be interesting to find out if this charge is equally applicable to biology, chemistry, mathematics, whatever. Now we could look at the class 11 and 12 syllabus, where there is some amount of discussion, but as I said, the majority of the students who are going to be social scientists would have left the school system by class 10. So I will skip over that portion about what the class 11 and 12 syllabi say. Now, given this situation, I'm not surprised that many social scientists are unaware of what's going on or what's happening in physics. They are ignorant about, or they have never been taught about modern developments in physics like quantum mechanics or special and general theory of relativity, particle physics, modern advances in cosmology, to say nothing about things like deterministic chaos, nonlinear equations, and complexity theory. So it is not the lack of awareness of these facts that I'm worried about. It's the lack of awareness of the concepts which you go with them. So if you never did any of these things, then therefore you are not familiar with any what you would call any modern concepts in physics, and that is what is the reason for my worry. So very often social scientists, even when they seem to be locked in the Newtonian paradigm, in which and this is true even of their critiques of science, because they still believe that science is overly mechanical, it's strongly deterministic, and extremely reductionist in its approach. And I think this is because they are not aware that science and physics in particular has moved away from this paradigm in the last 100 years. And I think that is the problem that I'm trying to address. Now, in order to do this, if you want to change the situation, we have many problems. Because I think it calls for a fresh look at the organizing principles of the school science curriculum, and to ask once again the fundamental question of what should be the basis for curricular choice. If you the standard answer to if you were to ask any of these curriculum framers, why should we teach science? Their answer would be, in class 9, 10, 11, 12 in school, their answer, I think, would most probably be that this is to train future scientists. If you press them harder, they might come up with answers like to produce better citizens in an increasingly science-driven society. They might even say to provide a liberal education for a rounded understanding of all the significant domains of knowledge. But even when they say that, they think that this is of a lower priority than the demands of the discipline itself. That means you must be teaching science in schools with a view to producing future scientists. But this serves but this would serve the interests of only 20% of the people. So what about the other 80%? Are we going to sacrifice their development as individuals, their development as responsible citizens at the altar of trying to train only those 20% who would be future scientists? And I think this is worth thinking about. This is something that's bothering me. I don't know whether you would join me in my analysis, but here is what I would say. That I believe it need not be this way. It is this way because you say that science and physics, let me talk about physics itself, is a very strongly hierarchical discipline, that you can't teach modern developments unless you've gone through the paraphernalia of developing Newtonian mechanics and all its glory, and only then do you prepare the ground for an understanding of modern developments in physics. That means that they are presuming that all the concepts that you come across in modern physics are in some sense rooted in classical mechanics, which is the pre-Newtonian physics that one talks about. But it is also acknowledged that there are paradigms in any discipline. For example, Kuhn was the first to point this out, that very often paradigms are distinguished by the fact that they are incommensurable. it is very difficult to make comparisons between the same words might mean different things in two different paradigms. So the question I'm asking is it possible to make use of this semi-autonomous nature of paradigms in order to be able to skip the historical and logical development of the subject and talk directly about modern developments without having to go through the rigors of the basic subject itself? And although it might be trivial, let me remind you that in schools mathematics, there are at least 3 different paradigms working. There is algebra, there is geometry, and then there is arithmetic. And although it is true that the 3 subjects are related in some sense, but it is also true that they can more or less be developed in parallel. It is not necessary that you first teach arithmetic, then you teach algebra, and then you teach geometry. So, in a sense, their autonomy can be used for skipping one, doing the other, or reordering the way in which this is taught. Now, I would like us to examine whether this can be used in the teaching of physics. For example, if you accept that these are independent, that they are paradigms in some sense, that classical mechanics forms one paradigm, quantum mechanics forms another, relativity theory forms a third, then the question to ask is it necessary to go through a sequential development of these subjects in order to, or a sequential development of of classical mechanics in order to be able to teach classical mechanics and relativity theory as aberrations of classical theory, in the sense that you first talk about the successes of the theory, you praise Newton and his deterministic vision, and towards the end you then start pointing out that there are problems if there are objects which are moving very fast, or if there are objects which are very small, and then classical mechanics starts breaking down. And that is how we introduce quantum mechanics, and that is how we introduce relativity. The question I'm asking is it necessary to do this? Can we not, apart from, I'm not saying ignore classical physics completely, but while you have done enough of classical physics, without waiting for its full flowering, can we not start talking about quantum mechanics and talking about relativity theory, not as aberrations or points of failure of classical mechanics, but as disciplines in their own right? That is the question that I would like to pose. Now, why is it important to do so? Let me give you a few examples. How much time do I have?
10 minutes.
So, just a few examples of why I think it's important not to wait for the full flowering of classical mechanics before taking on the other subjects. Because if you want to do that, if you want to progress systematically and logically and chronologically, then there is no question that you will not have time to do any of modern developments in the curricular load that which is within the capacity of children and which is possible to do in class 10. So we have to think of at least a development of physics up to class 10, which is different from the one that we have been following so far. So I forget about wave-particle duality, which essentially says that it addresses the old problem of whether light is a wave-like phenomena or is it made up of particles, and the resolution in quantum mechanics that not just light but all matter can display both particle-like and wave-like qualities depending upon how you interrogate the system, and depending upon your experimental arrangements, the same thing can show particle-like or wave-like behavior. That is, they are both particles and waves at the same time. Let us look at, what shall we look at? Heisenberg's uncertainty principle. Now, Newtonian mechanics, I would like to point out, assumes that it is possible to specify the position and the momentum of a particle to arbitrary high degrees of accuracy. And this permits you then to have well-defined trajectories in which you specify a set of initial conditions. You use Newton's laws of equations of motion, and given the initial conditions, you can predict the future and the past behavior of a particle to arbitrary degrees of accuracy. But quantum mechanics says that it is inherently impossible to do this. And why? Because of the uncertainty principle, which says that you cannot simultaneously specify to arbitrarily high degrees of accuracy both the position and momentum of a particle. And there are other such conjugate variables which you can't do it. Now, if this be so, which implies therefore that if I know the exact position of a particle, its momentum or its velocity becomes completely uncertain. And on the other hand, if I know exactly how fast a particle is moving, then its position becomes totally uncertain. That is the content of Heisenberg's principle. Now, if this be so, then we cannot define trajectories anymore in the precise sense that we were defining it earlier. And therefore, you cannot, this vision of being able to predict everything, the future of all particles, if I know the laws of force and the initial conditions, that Newtonian dream of strict determinism just lies shattered. Now, relativity theory. In classical physics, an object can move as fast as you like. Every object is characterized by its mass and its weight, and time flows majestically forward at a uniform rate for all observers. Now, this is not true in relativity theory, which starts with the assumption that the velocity of light is a universal constant, velocity of light in vacuum is a universal constant, and then whose implications then are that mass and position, that mass and dimensions of a particle, of a body, are no longer uniquely possible to characterize uniquely, in the sense that both the mass and dimension become functions of the speed with which the object is moving. So, as the object moves faster and faster, its mass increases, and its length in the direction in which it is moving gets shorter and shorter. So you cannot associate a unique mass and a unique dimension to any body which is moving at higher than conventional speeds. It also shows that mass is no longer conserved, because mass and energy now become interconvertible, and which is expressed in the most famous equation in physics, E equal to mc squared, which tells you how energy can be, explains to you why such large amounts of energy are released in atomic fission and fusion processes, because mass has been converted to energy. It is proportional to the square of the velocity. The velocity is very large of light. That is a very large number. So even small amounts of mass can give rise to large amounts of energy. Well, I have 5 more minutes. Let me forget about everything. Let me take a non-quantum mechanical, non-relativistic example. Let us talk about nonlinearity. Now, traditional physics, classical physics, has always taken any phenomena, and whether the relationship between the cause and effect is a linear one or not, it approximates it by a linear relationship. May be valid over only small domains, but that is what it does, because nonlinear equations, where the relationship between cause and effect is anything other than linear, that's what we call nonlinear equations, because nonlinear equations are are notoriously difficult to solve. So you linearize anything because your mathematical apparatus allows you to solve them very easily, make statements about it. But what is missed out is that if you give up the nonlinearity of the system, then you never encounter the condition that that sometimes the behavior of this system can become very sensitive to small changes in the initial condition. Now, classical physics is characterized by the fact that if I start two identical systems off together at this point and follow their development, they will never diverge very far away. They will more or less stay close together as the development goes on. But if there is, if it's a nonlinear system, and then although it can behave like this in certain regions of its total behavior, with a change in some control parameter, you can get into a nonlinear chaotic regime where although you might start from two identical systems very close to each other, because of the small difference in their initial specification, the behaviors might become totally different. So this extreme sensitivity to initial conditions has a name called the butterfly effect, and it's been usually paraphrased by saying that whether or not a butterfly flaps its wing in Bangalore today will determine whether there will be a thunderstorm in Chennai 3 days down the line. To give you another example to make this clear, I'm sure everybody knows that the rivers Narmada and the Son both start in, have their source in Amarkantak. Now, imagine it is raining in Amarkantak, and there are two raindrops which fall close to each other, but one lands in the catchment area of Narmada, and the other, even though separated by a few centimeters, lands in the catchment area of the Son. Then, because even though their initial conditions, initial situations were very similar, the drop which goes towards Narmada ends up in the Arabian Sea, whereas the other drop will probably end up in the Bay of Bengal. So that is what you mean by saying that the system has become very sensitive to small changes in the initial condition. And in a nonlinear system operating in its chaotic regime, this is not true only of isolated points, but all over the space in which you can specify the system. So again, you have questions about determinism and whether or not you can predict the future behavior of a system, things which are normally accepted in quantum mechanics. So what does my proposition boil down to? It is, can we forget Newton's equations of motion? Can we forget the classical concepts of space and time and start with a clean slate to develop concepts such as relativity and quantum mechanics and nonlinear phenomena? You don't dismiss it out of hand, because I think it is possible. But it requires a conscious act of sacrificing rigor and conceptual development for the sake of extending understandings about some extremely important concepts in physics which should be available to people without having to go through the rigors of a conceptual development of the subject. And this is the proposition I put before you. I think it is possible. I don't know whether it will be done, because in order to do this, you will have to convince the powers that be, which frame curricula for class 10 and 11, that this is a worthwhile and feasible exercise, and then hopefully 20 years down the line, maybe something will happen. Thank you.
So let's start with
what you say about social scientists not understanding the way natural science is built, or the amount of certainty and all, that's a worry. But I would have far more serious worries, one, of many kinds. One, of scientists not appreciating how social science works, or humanities work, and, for example, even philosophical concerns which drive not only other fields, but science itself. But these are anyway larger worries. But secondly, as if it's just the whim of the curriculum makers that's limiting all the relativity theory and Heisenberg's principle and so on and so forth. It's just their classical whim because of which it's happening, and it seems as if the concern for children seems to be completely missing. I mean, if you see the curriculum today, why just the particle nature of matter, why this chair is not, it's just full of holes, is something, it's shifted to 9th simply because children find it very, very hard to comprehend earlier. And even when you bring it in class 9, the planetary model of the atom has to persist for a little while, because the atom with the cloud around of electrons and etc. is just too hard for children to comprehend. Any educator who has dealt with this knows it's a hard exercise to get into the micro world and to get to the macro speeds of the kind relativity theory would require. So it's like we from the world as we experience it to the world which is beyond intuition is a very hard journey. And I don't, already when our children are so loaded badly with curricular load, to say that introduce concepts which are even hard for BSc students, I mean, I have a serious discomfort with this proposition itself.
Okay, shall we take a set of few questions? I have a feeling that some others might also say something similar, so in which case you could put. So let's take about 3 or 4. I have 3 here and 2 here. So let's do. Thank you.
Thank you, Vijay, and yours is certainly a very bold suggestion. And speaking as one who crossed over from science to social studies, social science, my gut feeling is that even if your suggestion is adopted, the animosity you talk about will not go away, because there are many other reasons for that animosity. So the solution that you're proposing will not really be helpful, and there are many reasons, and I'll just talk about 2, because okay, so then I'll just talk about 1. Yes, okay, briefly 1. And I do qualitative research, and what we find is that scientific research has emerged as a template to which everybody, all kinds of research should aspire to if you want to get funds, and that has become very oppressive to people who do other kinds of research. So that in itself generates a lot of ill will. And then there are other reasons, but I'll continue. Yes.
Yeah. Hi. Yeah. Actually, I was not too comfortable with your claim that that it's only up to the 9-10 standard level that social scientists have an idea of, and that is what they are basing the critiques on. I mean, like, I believe it's kind of opposite. In fact, most of the critiques that I've read of science is of the undergraduate, what I would consider undergraduate level, and. So, for example, when you look at nuclear science, nuclear physics, and atomic and molecular physics, and all, that kind of paradigm, that framework of looking at science is essentially for state. I mean, it only benefits the state, and it is driven. It is like military-driven technologies, which is from which this framework of science develops. For example, if a person specializes in nuclear physics, what else can a person do? It does not make the person a better individual. It just makes a person capable of only working in a nuclear power plant. Secondly, the thermodynamics that came out from the need to develop steam engines during the industrialization.
Okay, sorry, you'll have to make a specific question, please,
okay,
because I need to get back to that.
So my point is that I actually, it's a disagreement that I don't agree that it's only the 9th standard syllabus. It's mostly the undergraduate level, the nature of science itself, which is being critiqued. And I still feel it is reductionist, and in addition, it is also intrusive. It is violent against nature. There's also epistemic violence that comes into science, and also the nature is quite arrogant when you talk about laws of physics. You talk about indivisibility of atoms. And regarding reductionist, I mean, the Higgs boson.
I think that's an entirely different lecture altogether. I think your message has been clearly coming in. We'll take one more question, and then he will respond, and then we'll take the second set. Yeah.
This is more a reaction to the first comment. I'm going back to my own childhood. I had given up on physics in class 10 by the time I reached 8, 9, 10. And it's only in class 10. And the lady was saying that children will not comprehend this kind of relativity or the other Heisenberg's this. She had given me just a book, The Dances of Woolly Master. Whether you agree with the contents and how it is presented, that's an entirely different matter. But that is probably the reason that I stayed with science rather than without it. This. So it's not really. I mean, we should not underestimate today's children. Their comprehension levels are good, provided it is presented in an interesting manner. Physics doesn't have to be so dry and cut out kind of thing, the way it is currently taught.
Yeah, I'll try and be brief in what I say. With regard to your objection, I agree absolutely. I'm not trying to make the claim that physicists are any better than social scientists. All I'm saying is, I was making the point that it is important to address this question of ignorance about modern ideas, whether it's been physics or in sociology or economics or wherever. We have to address the problem of how to make the non-technical, non-specialist population aware of some of the new ideas that come through. And if you're going to stop general discourse on various disciplines at the class 10 level, then you have a genuine problem of how to tackle this question. I don't entirely, I agree with the suggestion there. I think you are looking too much, you are a slave of the present dispensation. I think you should, this is why I say, can we forget about what we are doing at the moment? I am not saying that you bring down everything into the classroom. It's not possible. So you have to be selective. You have to decide which are the important ideas that you want to convey, and then try and do it in something which is not so rigidly technical or rigidly logical, but talk a little more about the non-logical, as people were saying, the other aspects of science which can come about but are not done at the moment. Ajay, I mean, what do I say? The idea is not to just to relieve all possible animosities between social science and science. I know that there are many other causes, but at least ignorance about each other's discipline. And I would repeat, it's not just only part of social scientists not knowing about science, but scientists equally not knowing about social science. It is this removal of this ignorance that I think is important if you want to promote a more civilized discourse between the two.
I was just wondering, what happens to the history of an idea? Like, as much as it is important to study the present ideas, the contemporary new inventions or discoveries, isn't it also important to know the history of an idea and what is the thought process that went into the creation of that idea? And also, like, when you said about Heisenberg's principle, why did that uncertainty principle come into existence? Like, there were a few experiments which could not be proved, and that is why the Heisenberg principle, Bohr, I think, thought about the uncertainty principle. So what happens to the history of idea? Because the history of an idea as well makes science so much more interesting. So, any comments on that?
Vijay, actually what you're saying seems very interesting, but what I don't understand is what is your basic question? Because what you would say then is that the physics students should get basic glimpses of the debates in history, should get basic glimpses of the debates and cutting ideas in economics and in sociology. Because you seem to be premising your argument on the fact that the disconnect does not arise because of the way science has dominated, which is what many people are trying to say, and the way it has tried to monopolize the space for thought, and the animosity arises from ignorance of. So if that be so, then we are asking a very important question, that the entire structure of general secondary education should change. but you also would recognize yourself the danger of, popularizing all concepts to the extent that when you come to doing some subjects rigorously, there is a mismatch between what you've learnt about probability, what you've learnt about Heisenberg uncertainty, and what it is actually. So there is that danger also. So I'm not sure where you're placing your justification for doing this as a part of general education. That's what I understand you saying.
Yeah, you can. Yeah, I think we are almost done.
To answer Hardy, of course, when I say that you should do this with physics, I imply that you should do it across subjects at the class 9 and 10 level. That you should pick up, what you should do is pick out the important ideas which are considered important, not just for the future development of that subject, but as a body of knowledge which is shared amongst the whole of the population, and which is considered important, and that is where the task of the curriculum framers will come in. But this is not to, I'm not advocating diluting the discipline, because you already have a structure which says that the disciplinary development of any subjects starts at the class 11 level. And I'm not making a plea that this philosophy of education, if you can call it that I'm propagating for class 9 and 10 should be applicable at the class 11, 12 level as well. All I'm saying is that realize that most of your students are going to give up their disciplinary concerns, or rather take up their disciplinary concerns only after class 10. The few of them that stay on for higher education. So if you're worried about doing justice to the calls of the discipline, start it at class 10. Start it at class 11. Why need you to do it at class 9 and 10? In any case, I think there are other models in which the kind of disciplinary development you're talking about does not take place at the class 9 and 10 level, but starts only at class 11. And I think the answer to your question is similar. I'm not saying that you should not teach about the history of a discipline or the history of ideas or the history of concepts, but why do you have to do it at class 9 and 10? You have the rest of your life as a student to learn all these things. And I think even if you start in class 11 and you frame your curriculum properly, you drop out things which are not absolutely necessary, you should find time to look at the history of ideas, the history of concepts, and distinguish between what is chaff and what is grain, and concentrate on the grain rather than the chaff.
Okay, we'll have the last question, yeah. Okay, Ravi, last two questions, Ravi and then.
Struck by the distance, the position you're taking today from the one which was taken in the early Eclave experiments of keeping education close to experience. I think that's so. So I'm saying, I mean, it's quite a long distance. So how do you see that?
So I was just wondering, you were talking about how there's complete ignorance about each other's disciplines between the men of science and people of from the social science disciplines. And I was wondering whether it was just a function of the curriculum and that it stopped teaching later developments, or it was the notion of expertise that surrounds science and which is kept up by the discipline itself to exert certain amounts of control and to, for instance, if you think of the GM foods debate, so what happens is that science tells you the right answers and people from outside of the discipline can't engage in these, what are essentially public debates. So I was thinking about when the liberal arts student or the social science person stays out of reading any material at a time of leisure, for instance. Like, for instance, a person who's an anthropologist will read history, will read several other things which are accessible to him or her, but they won't read even popular science usually, even if it's accessible, because notions of expertise are upheld around the discipline. And I was wondering whether it's this aspect that keeps people away and furthers this cleavage more than the fact that that in school they didn't learn updated versions.
Can you specify your question more precisely? Because I've heard a lot of comments, I don't know what.
Okay, so my question essentially is, do you feel that the cleavage between people of science and people from the social science currently, and the animosity across, is because school education stopped at a particular level and didn't take into consideration advances in the discipline of science? Or do you believe it's because of the notion of expertise that's kept around science that distances people from...
Okay, I think we'll stop at that question. We are run out of time. But before you respond, just to add to what she's saying, perhaps, the fact, for example, that a lot of people, since you spoke specifically of physics, the fact that the expertise of mathematics, for example, is just needed, which we hear people are not able to deal with, also makes people move away from physics in the context of expertise, that they don't understand mathematics, so they are not able to understand something. So it is in this larger context of what training you need in order to be able to jump to that quantum before you do the classical. And that seems to lead to this alienation. I'm just adding to that, but I think we'll have a final word from you since we have run out of time. So please go ahead and respond to both Ravi's and that question. We are really out of time.
First, can I answer Ravi? You are essentially saying that what we did in the Hoshangabad program was a kind of philosophy of education that we were promoting across all years. This is just not so. The philosophy that we advocated was for teaching science in middle school, in predominantly rural areas, in a resource-starved environment. And that it was important in the context of Indian science education to be able to demonstrate that experimentation and activity in the classroom are essential features for learning science, and it is possible to do so even in a deprived rural environment, provided you make sure that appropriate kits and things are available. I think it's a misinterpretation to think that this philosophy that we're advocating for middle school was in fact applicable throughout, because the insistence on knowledge arising from experimentation clearly could not have been carried out at the higher levels. There are critical experiments in science which you will never be able to reproduce in the classroom, however much you try. But at the level at which we are dealing, at the middle school level, we demonstrated that you could find enough and interesting activity which children could do and which could form a basis on which they would learn about not only the products of science but the methods of science. Okay. I've now forgotten what I'm trying to answer there. Yeah, but what is it that bothers you? I mean, I am saying that there are many reasons for this. I've conceded that when Ajay said that their ignorance of each other's subject is not the only reason for animosity. Fine, but does the ignorance exist? And is it a good thing to allow it to exist? Or should we try and address this situation, and within whatever limited capabilities we have, we should try and remove that, and hopefully then it will lead to a better understanding between the problems of each other's disciplines and a better appreciation of what is going on. Yeah.
So no, I think we'll continue this conversation because I'm sure there are many other comments.
Can we meet outside? Thank you.
Thank you, Verma. Thank you so much. Thank you all for being here.